right, so generally what I do is the way I start things is I usually put the date on there. So today is January 20th. All right, and then whatever section we are covering, all right, I usually write the section numbers. So we're starting, all right, with 5-2 and section 5 dash, sorry, I said 5-2 and I wrote 5-1. Section 5-1 and section 5-2, okay? Now, if you took 104, all right, then you did a lot of this stuff. You should have covered 501 or 5-1 and 5-2 in that 104 class. So that's why they put them together. They're assuming that this is review. If you're taking Math 105, this is like your first math class in, they're assuming that because you passed your math placement test at a good enough level, then you already also know this material as well. All right, but basically it's polynomials. Okay, so anything and everything about polynomials. So you can evaluate them. You should know things like vocabulary words like binomial, trinomial, monomial. You should be able to put a polynomial in standard form. You should be able to evaluate any type of polynomial. And if we use polynomial functions. Okay, now I am going to talk a little bit about the degree because that seems to be, I mean, you learn it and then everybody forgets it. Okay, but it becomes very, very important when we're trying to sketch these polynomials. Okay, so let's suppose we have, I'm going to do two different examples here. We'll do it in a single variable. If I had something like a negative 4x to the 5th plus a 6x to the 4th minus 2x to the 3rd minus 3x squared plus 9x minus 10. Okay, yeah, I got a little ridiculous there. Okay, but you get the idea. All right, this is in a single variable. This is what you would have done in an Algebra 1 class in high school, or you would have done this possibly even in Algebra 2. But this is what standard form looks like. Okay, so we can write down standard form. And it's standard form because the exponents are in decreasing order. All right, if it's in standard form, then I can look at the very first term, and that is called my leading term. Okay, so a little bit more vocab right there. All right, from that, then I could be a little bit more specific and I could find my leading coefficient. All right, so leading coefficient is the -4 because that's just the number that's in front. All right, and then the exponent right there is a 5, so the degree of this polynomial is 5. All right, and so being able to identify all of those parts, all right, is important. And now this would be the easiest type because it's in a single variable. All right, if I had an example that had more than one variable, then that's when it gets a little bit more challenging. So I could have something like a 7x squared y to the 3rd minus a 10x y to the 6th plus an 8x to the 3rd y to the 7th. Let's not get too serious about this. Let's just stop with 3 terms. Okay, but clearly it's a polynomial curve and I'm in multiple variables here. Okay, so what you have to do to find the leading term and to find the leading coefficient and the degree is to find the degree of each individual term. Okay, so I'm going to take this first term. Terms are things that are all multiplied together and then separated by plus or minus signs. Okay, so that means that this is a term, this is a term, and this is a term separated by that minus sign and that plus sign right there. What I'm going to do is I'm going to take these two exponents and add them up. 2 plus 3 is 5, so the degree of that term is 5. Okay, if I think of the imaginary one that's right there, I add up the 6 and the 1, the degree of this term is 7. All right, if I add up the 7 and the 3 right here, that's 10. So that term has a degree of 10. Okay, now, whichever term has the highest degree, that is my leading term. So since this is a degree of 10, then that one right there is my leading term. once I've identified the leading term, I know that the degree now of the entire polynomial is 10. All right. And then the leading coefficient is an 8. Okay. So in the past, I have always put this information on test number 1. Okay. Because it leads into the sketching of the polynomials. Okay. All right. So anybody have any questions yet? I will take silence as a we're all good. Okay. All right. Okay. Now, you should be able to evaluate polynomials. You ought to recognize polynomial function notation. All right. So let's do a little function notation. Okay, so function notation just means it's that f of x thing that hangs out at the beginning. So if I did f of x equals, maybe say, let's do something really small so we can do the math in our head, 4x squared plus 2x minus 1. Okay, so if I looked at this in terms of function notation, and then I asked you to evaluate, maybe say, f of, let's again keep the numbers pretty small here, f of 3. All right, so hopefully you remember this. This just tells you take that 3, put it into the f function. So here's my f function. So if I was going to work this out, then I would have f of 3 is equal to, take the 3, plug it in to the function every place there is an x. So 4 times 3 squared plus 2 times 3 plus 1. That's going to be a 9. That's going to be a 36. This is 6. Don't let me make a silly mistake here. That's going to be 7.
Excuse me, Professor. Is it +1 or -1?
Oh, thank you. See, you got to keep me awake because this time of the evening I do make mistakes. Thank you very much for catching that. All right. All right. So it is -1. All right. So it's a -1. So then I'm going to have a 36 plus a 5. We can add that up. Should be about a 41. All right, now obviously if you've got a calculator and you really know how to use that graphing calculator, you could put this function in your y1 and have it do it for you, or you could just type this left to right in the calculator and work it out that way. All right, so lots of things there, but this is just kind of review, making sure that you know how to do function notation. All right, let's go ahead and go to a new piece of paper, I think, because I'm going to write, I want this all to go together. All right, so let's take a look at the graphs. All right, polynomial functions of degree 2 or higher have graphs that are, and then here's kind of 2 vocab words, that are continuous and smooth. Okay, so that's just in general. Okay, polynomial functions, when I graph them, they are smooth and they're continuous. So that means I ought to be able to give you a bunch of graphs or sketches, and then you should be able to tell me, yes, it's a polynomial function, or no, it's not a polynomial function. All right, so just as a variety of examples here. Okay, if I did something like this. All right, now you watched me draw it. Okay, so was I able to draw the entire thing without lifting my pencil? Yep. All right, is it smooth? Yes, it does not have any jagged points. These are all curves and they're nice and smooth. So yes, this is a polynomial function, okay, because it's continuous and it's smooth. All right, now if I had drawn something like this, we'll try to get this all in the same one. If I would have drawn something like, say that's -2. if I would have drawn something like that, obviously you watched me draw it. All right. But if I would just look at this, okay, ask yourself, is it smooth? Is it continuous? Well, it's not continuous because what did I do? I drew this section first, then I lifted my pencil completely, and then I drew this. All right. So it's not continuous. If it's not continuous, it can't be a polynomial function. All right. It's also not smooth because right there is very clearly a jagged point. All right. Now, if we want to be a little more specific about that, all right, that's called a cusp. All right. And we're going to call it sharp point, but mathematically it's a cusp. All right. And then right in here where the graph does this funky thing. All right. Obviously I lifted my pencil to draw the rest of it, but this is what's known as a jump. All right. And that's obviously higher level mathematics, like on into your calculus classes and pre-calc classes. But the idea here is because of the jump and because of the cusp, this is not a polynomial function. All right, so just taking a look at the graphs, all right, and I generally talk a little bit more about this because this is stuff that probably wasn't covered in high school as much as some of the other stuff. So not only can I look at the graphs of our polynomial functions, but I could look at just the equations and determine whether or not it's a polynomial function. All right, so I'll give you factored form and standard form of polynomial functions. Okay, so polynomial functions. All right, so we've already seen standard form, right? So we'll do a nice short one like 2x squared plus 3x minus 1. Okay, so that's obviously in standard form. We've already talked about that. I gave you an example of that one earlier. Okay, now you could also see something that looked like maybe say an x plus 2 and then an x minus 3. Let's see, just make it as simple as that. All right. This you should recognize as a trinomial that has been factored. All right. So this is factored form of a polynomial. Okay. So I know just by looking at the equation that I have polynomial curves. All right. Now, when do I not have polynomial curves? All right. So these are not polynomial curves or polynomial functions. Words are interchangeable. Okay. So if I had something that looked like f of x is equal to maybe say a 5 square root of an x minus 2. All right. I mean, it kind of looks like that, but there's a distinct rule. All right. If I have radicals, all right, hopefully from previous courses, you know that you can go back and forth between radical form and exponential form. All right. So technically, I could rewrite this as 5x raised to the 1/2 power. All right. Well, as soon as I do that, this exponent is not a whole number. All right. It's not a whole number. Not a whole number. All right, if that's not a whole number, then it's not a polynomial curve. So that's basically what you're looking for. You're looking for exponents that are not a whole number. So another example would be if I did something like maybe say a 1 over an x squared plus a 3x. Okay, rational right here, okay, but stop and think about your laws of exponents. All right, this course is going to expect you to be able to pull from previous knowledge. All right, if I take an x squared and I move it to the top, that's the laws of exponents, it becomes negative. So I could technically rewrite this as x to the negative 2. All right, and then as soon as I do that, that negative 2 exponent is not a whole number. So that's why this is not a polynomial function. This is not a polynomial function. So again, kind of really, as long as you have the rules, I ought to be able to give you a bunch of different expressions, and then you tell me, yes, it's a polynomial function, or no, it's not a polynomial function. Okay. Now the rest of what's in section 5.1 is it talks about the leading coefficient test. It talks about sketching polynomial curves. You don't have to do a lot with that right now. I would definitely read in detail, all right, pages 6 and 7, okay, in the notes of section 5-1 of my online notes. All right, that talks about the leading coefficient test. It talks about end behavior. All right, so that you can do some rough sketches. All right, page 8 is some practice problems. All right, that you can try to see if you have mastered the leading coefficient test and that end behavior. So in the notes, there's a matching section. All right, this right here has always been on test number 1. Okay, I always put something like that on test number 1 every time. All right, but other than that, that kind of pretty much finishes 5-1, except for straight adding, subtracting polynomial curves. Okay, which that's no more than adding and subtracting like terms. So I'm thinking you're pretty good with that. So we're going to kind of do a combination of multiplying and adding and subtracting all together. All right, so we'll start section 5-2, but keep in mind, what did I tell you? I told you section 5-2 is like 14 pages long. So you're definitely going to need to download the online notes and go over anything that we don't get covered. Okay. All right, what are we doing here? We're about 4:40, so we're not too bad. All right, so let's start out with a little bit of adding and subtracting polynomials. Okay, now obviously there could be straightforward, easy ones, all right, or because it's college algebra, they can step it up a little bit and make the problems a little bit more challenging than normal. Okay, so let's start out with an easy one and then work our way up. Okay, so you might see a problem like a 5x to the third y minus a 2xy squared plus, let's do a 7y. All right, and if I'm adding and subtracting polynomials, you would have those parentheses around that to indicate that that's a polynomial. Now let's suppose I'm subtracting then the polynomial of 8x to the third y plus a 9xy squared. And then let's do like a minus 5x, just to be different. All right, so I need to go through and find like terms. All right, for like terms and lots of variables like this, you have to have both the base and the exponents all matching. Okay, so we've got an x to the third y and an x to the third y. So this term and this term is alike. Okay, so I will be putting those two together. All right, the xy squared, all right, that one and that xy squared, those are like terms, so I'll be putting those together. All right, and then the 7y and this 5x sitting right there are not like terms, so they will be just extra terms, individual terms that I put through here. Now, with this being a minus, I mean, I don't care if you totally rewrite or if you just maybe do it above it, okay? But you do have to remember that what this is, this goes through and changes all those signs. So a lot of people, so that we don't have to like do lots of work, you don't have to rewrite the whole thing. You could do a minus 8x to the third y, and then you could do minus 9xy squared, and then you could do plus 5x. All right, that just prevents you from having to write the whole entire thing out again. All right, let's go ahead and put these together. This will give me a -3. So I deal with the coefficients. I leave bases and exponents the same. So the x to the third y stays the same. And again, don't let me make any mistakes here. All right, this is a -2. This is a -9. So I'm going to put those together at -11. And then all the variables and all the exponents remain the same. Now, personally, probably what I would do is we have a tendency to put polynomials in alphabetical order, but this comes first and then this comes second. So in all honesty, I'm not going to be overly picky on the order in which you put the terms. So some people would read left to right and would put this term and then this one. Others are going to go alphabetical order. It doesn't matter. All right. It really, honestly, to me, does not matter. Okay. They're equivalent answers. Okay, so that's why I said this, adding and subtracting polynomial curves. I did subtracting because that tends to be the hardest. It's the exact same thing as adding. All right, now that would have been standard Algebra 1, Algebra 2 pre-calc, all right, from high school. Now, since it's college algebra and you're in a book, the Blitzer book they're going to do some funky things with the exponents. All right, so a 2x raised to the 2n. They're going to start putting exponents that have variables in them. Okay, not a big deal. All right, plus 2x to the n, and then maybe say a minus 9. Let's go ahead and do another subtraction. Let's say a 6x raised to the 2n minus a 4x to the n, and then minus 4. Okay, so that just looks a little bit different. Instead of having bases, it's variables, and then exponents that are numbers, there's just some variables up there. Okay, does not change the problem at all. All right, I'm still going to look for bases and exponents that match. This is an x to the 2n. This is an x to the 2n. So those are my like terms. Okay, then this one has an x to the n power, and this has an x to the n power. So these are my like terms. Okay, and then obviously anytime I have constants, all right, this is just a plain minus 9. This is a plain minus 4. So those go together. And again here, let's, this is a minus. So I need to remember to go through and change all the signs. So this is a minus 6x raised to the 2n. It's a plus 4x to the n, and it's a plus 4. So it goes through, changes all the signs. Okay. And then I'm put my like terms together. So this is a 2 and a negative 6. That'll be a negative 4 x to the 2n. All right, just like we kept the same bases and exponents here, I keep the same bases and exponents here. Putting these two together, I'm going to get a 6, and then the same base and the same exponent. And putting together the negative 9 and the 4, that's going to give me 5 minus 5. Okay, looks pretty good. I'm glancing at my online notes. Okay, my online notes are wrong in this example. Okay, so this is the right answer right there. All right, so again, straightforward type questions you've done before, beefing it up a little bit because now this is college algebra. Now, in the My Math Lab, you are going to see questions that take this and put it in words. Okay, that's okay. We can do it if it's in words. They're just wanting to see if you can read a little bit here. All right, so they may say something like subtract 8x squared y plus 6y from the sum of a negative 2x squared y minus 6y squared and a 5x squared y plus an 8y squared. All right, so instead of writing it to you, showing you the problem as it would be traditionally written with just math, they're just putting it in words. All right, it says subtract this. All right, that's a binomial. So subtract this binomial from the sum, okay, the sum of this binomial and this binomial. All right, so then basically you've got to be able to take that sentence, translate it into what the problem is. Okay, so I'm subtracting that from the sum of these two. So I should add these two first. Logically, that makes sense. So I'm going to actually write the problem out and then we'll work it out. So if I've got to add these two polynomials, all right, so I'll have a negative 2x squared y minus the 6y squared. I'm going to add to that the second polynomial, 5x squared y plus the 8y squared. All right, I need to add this first, and then I'm going to subtract the 8x squared y plus the 6y squared. All right, so that sentence translates into this expression. I need to add this, and then I can subtract whatever's left over there. Putting the parentheses in the right spot make a difference, because if you don't put the parentheses around that, you're not going to know to distribute the negative. All right, you need to add this first just to see what you kind of come up with, okay, and then go from there. So I'm going to put my like terms together. These two are like terms, so I'm going to have a 3x squared y. These two are like terms, so I'll have a 2y squared. All right, now I'm going to go ahead and distribute that negative through, so I'm going to go change my signs. So minus 8x squared y minus a 6y squared. All right, at this point, all right, even though I did go ahead and put that set of parentheses around there, I really didn't need to because, all right, I'm ready to put my like terms together. All right, these two things are together. So that'll be a negative 5x squared y. These two will be a minus 4y squared. Okay, so just different ways that they're going to take the information that you already know and present it to you in a different type of problem. Obviously, I'm not going to be able to do an example of everything you're going to see in my math lab. The one thing that I would encourage you, especially if you did not take the 104 class, you're going to have question help available to you on the My Math Lab. So if you are stuck on something, take advantage of that question help. All right. Now you should also be able to multiply. I think I hit the adding pretty good there. Multiplying polynomials. And technically this is starting section 5-2. Okay. Now to be able to do that, you've got to remember some of your laws of exponents. All right. There was a lot of them. Obviously you wouldn't need every one of them, but you're going to need some. Okay. So, let's do a little bit of review here with laws of exponents. All right, the main one is when multiplying like bases, we add those exponents. All right, so I'll just start out with actually a pretty long one. We don't want to always do easy problems as examples. So let's do like a negative 6, x to the third, y to the fourth, z to the fifth, and then multiply that by 3, x squared, y, z to the, I haven't used a 6 there as an exponent yet. Okay, so my laws of exponents apply only to my exponents. When multiplying like bases, add the exponents. Keep in mind there's an imaginary 1 exponent right there on the y. All right, I do not apply any strange rule to the coefficients. So those two coefficients, all right, I'm multiplying, right? So I'm just going to multiply those like normal. So that's going to give me a negative 18. All right, now I'm going to do my laws of exponents. When I multiply like bases, I add the exponents. So that'll be an x to the fifth. On the y, as long as you don't forget the 1 right there, multiplying that will give you a y to the fifth. All right, and then adding those exponents on the z, that would be a z to the 11th. All right, so that is a prerequisite skill needed to be able to do these multiplying of polynomials. Now, that one was a pretty straightforward one. Again, could I put some letters in my exponents? Okay, I could. And I could even make it so that they aren't the same. All right, so let's do something like that. Let's do like a 2x to the 3a, and then a y to the 4b. And let's say we're going to multiply that by a 3x to the 5a and a y to the 6c. All right, just trying to be as creative as I possibly can here. Coefficients, okay, we multiply like normal, 2 times 3, that's 6. All right, now when multiplying like bases, I add the exponents. All right, well, can I add a 3a and a 5a? Yep, that's going to be like adding like terms. So that's going to be an 8a. So that would be an x raised to the 8a. Now, when I take a look at my like bases on the y's, I have to add 4b and 6c. They're not like terms. That's okay. I can still add them. I can show that I am adding them. I could put a little parentheses around them. I could do 4b plus 6c and then have that entire thing be the exponent. Okay. It's, do you understand what the rule is? Can you apply it to whatever they give you? When multiplying like bases, add those exponents. That's the best way I can add it. Okay, so just trying to show some different types of scenarios with that. All right, now, if we take this prerequisite skill and then put it into our multiplying our polynomials. Okay, so again, we can start out with really simple ones where we've got one term on the outside, multiple terms on the inside. We can do it with single variable versus multi-variables, I suppose you would do it. So they might say multiply. Let's just say the directions say multiply. I don't think they're going to say anything else. Okay. Let's go back and do a really, really easy one, and then we'll work our way up. So let's do like a 4x to the third, 2x squared plus 3x minus 7. Okay, this would be like a really, really simple one all the way back to Algebra 1. All right, now I honestly like to call this just using the distributive property. You take what's on the outside and multiply it by everything that is on the inside. All right, generally when I first teach this for the first time, I use the little arrows just so people can remember what I'm doing here. So I'm going to multiply my coefficients. I'm going to add the exponents. Okay, so this is going to be an 8x to the 5th. All right, doing the second one here, 12x to the, you don't want to forget the imaginary 1 that's sitting right there. So that'd be an x to the 4th. All right, and then with the minus sign there, that'll be a minus 28. And then the x to the 3rd. Okay, so that would have been all the way back to, like, say, in Algebra 1. And then from here, they just kind of get crazy. I can put 2 terms out here. I can put more than 3 terms in here. If I do just 2 terms on the inside, 2 terms on the outside, we know that is FOIL. All right, you've been foiling for a long time. All right, but really, FOIL is the same thing as repeated distributive property. Okay, so I could do a 2x squared minus a 3 times a 4x minus 5. All right, so this is a binomial times a binomial, but binomials are still polynomials. All right, you can do FOIL, you can do repeated distributive property. It really doesn't make any difference how you do this one. All right, real quickly, I'll go ahead and show the FOIL. That would be first terms. That's going to be an 8x to the 3rd. Then I'm going to do outside terms, the ones on the far outside, so a minus 10x squared. Inside terms, minus 12x. And then the last 2 terms will be a positive 15. Oh, and the way that this one was set up, I don't have any like terms. If I would have had some like terms in the middle, then I would have had to keep going and add some like terms. But on this one, I didn't have to do that. Okay. Let's do one with maybe say 2 on the outside, 3 on the inside. All right. And again, there's a lot of different methods. Some people just kind of string it out left to right. Other people's do more of a vertical method. All right. So you have your choice. These were all single variables. Let's throw in like 2 variables. Okay. So let's do like a 7x squared y plus a 2x. All right. And let's multiply that by a 3xy to the 4th minus 2xy squared plus 3x squared y to the 3rd. All right, again, I'm just randomly making these up. They're just polynomials. All right, now, like I said, you could do this either totally 100% horizontally across your paper, all right, which that kind of gets really, really, really long. So I have a tendency to do a vertical method. All right, but the concept is the same no matter how you write your work down. This first term needs to be multiplied by everything in the second one. Okay, so I'm going to color code this. All right, so let's do this. So this will be a 21 and then x to the 3rd, y to the 5th. Keep me honest here that I don't make a mistake. All right, this will be a minus 14, x to the 3rd, y to the 3rd. Multiplying the first one with this last one over here will be a plus 21, x to the 4th, a y to the 4th. All right, now I've done all of that in red. Now I'm going to change. I'm going to color code this. Okay, now I don't know that I'm going to get any like terms. All right, sometimes I get like terms, sometimes I don't when I randomly make this up. All right, on this one, I'm going to have an x squared y to the 4th. I don't have one of those terms, so the vertical method is not going to help here. If I do this one, I'll have an x squared y squared. Again, not going to have any, so the vertical method's not going to work. If I did here, I'd have an x to the 3rd and a y to the 3rd. All right, now that one I do have right here. So this one is not the best one to show that vertical method. So I am going to keep going straight across here. Okay, so minus 6x squared y to the fourth, multiplying here, minus 4x squared y squared. All right, multiplying on the last one, plus 6x to the third, y to the third. All right, and then had I had lots of things that would have matched up, I could have done a vertical method, but since I didn't, that's okay. All right, where's my little highlighter here? So really the only like terms that I have is the x third, y the third, x the third, y the third. So I really only have two scenarios here that have like terms that I have to combine. All right, so an overall final answer. Again, I'm not going to worry about the order in which I place the terms. Okay, putting these two together, that'll be a minus 8 x to the third, y to the third. All right, plus a 21. Matter of just writing the rest of these down here. Plus a 6 x squared y to the fourth, minus a 4 x squared y squared. All right, now I'm hoping you're all paying attention and following with me and you didn't let me make any silly mistakes. All right, that I would say that's the number one drawback. All right, you're going to accidentally multiply something wrong. You're going to add some exponents wrong. You're going to miss the imaginary ones there when you're adding your exponents. So it's not going to be a matter of, oh, you're missing these questions because you don't understand them. It's going to be more along the lines of you made a silly mistake. Okay, now, a lot of what's in this section 5-2, they talk about special products. They talk about squaring a binomial. All right, and there's formulas for all of those that you can memorize. And we will do that one in particular. They're going to show you how to do the product of the sum or difference of two terms. Again, they give you a formula where if you want to memorize the formula, you can. But if you understand repeated distributive property, you can do that just as easily without the formula. The formulas do come in handy for factoring in the next chapter. Okay, that's the only good thing I can say about the formulas. All right, so let's do the squaring the binomial because that one people tend to miss more than the others. All right, so let's just call it squaring a binomial. Okay, so, and I'm going to do a real simple one here just so that you can see how people miss this all the time. All right, if I just had like an x plus 5 to the second power, okay? Now, the wrong way, I see this all the time as answers. All right, someone takes x plus 5, all right, and then they are thinking about, oh, I've got these laws of exponents, so I can just, power raised to a power, and they do this, oh, I can square my x and I can square the 5. So then I have people that write down x squared plus 25 all the time, okay? That is definitely the wrong thing because I cannot use power raised to a power because of that plus sign right there. So that law of exponent does not work. Okay. What you do have to do is you have to take a look at this base. The x plus 5 is the entire base and it is being squared, which means if I had a random number 4 squared, well, what would I do? I would take the 4 and I would write it down 2 times and multiply it, right? So that concept I have to apply to the algebra. So x plus 5 times x plus 5, all right, which now means what? I'm going to do FOIL, which will be an x squared. And if I'm showing all my steps, it would be a, oh, shoot, not a 10. That's me doing it in my head. I don't want to do it. I'm going to show all the steps. All right, then it would be a 5x plus a 5x plus a 25, which then would be an x squared plus 10x plus 25. Okay, so clearly you can see this is the wrong answer because it doesn't have that middle term. Okay, and so make sure you have the word wrong on that. I don't want you doing that. Okay, but this is a very, very important concept because people miss it all the time. So that one's kind of important. And then let's see, is there another one that's really super duper important? I think I do want to touch on, how am I doing on time? I'm still good. It's only about 5 after. Okay. It's really going to be helpful for you if you recognize multiplying to, a binomial, one with a plus, one with a minus. Okay, so in other words, if I had an x, let's do it with an easy one first here, like an x plus a 7 and an x minus a 7. Okay, same first terms, same second terms. I got a plus and a minus. All right, if you know how to factor the difference of two squares, all right, if I had an x squared minus 25 and I was factoring this, what does that factor into? Hopefully you have that memorized. It factors into an x plus a 5 and an x minus a 5, right? Two binomials. First terms match, second terms match, and one's a plus and one's a minus. All right, so if I recognize this answer, if I recognize this answer as being the answer to a binomial that has been factored, the difference of two squares, then all I have to do is square the first one. So x times x is x squared. I know it's going to be the difference of two squares. So put down a minus sign and then take 7 times 7. 7 times 7 is 49. All right, it's just a really fast way to do it. You're recognizing the fact that this right here is the answer to a difference of two squares that has been factored. Now, could I FOIL it? Yep, I could FOIL it if I wanted to. And then what's going to happen? I'm going to have a positive 7x and a minus 7x. Those two terms are going to cross out. The middle stuff just crosses out. So you can FOIL it, okay? But what if they took this concept now and put it and made it a little more fancy, all right? Again, you could use repeated distributive property, or you could use this formula, this idea of factoring the difference of two squares. All right, what if they gave you something like a 7x plus a 5 plus a 4y, and then they did a 7x plus a 5 minus a 4y. All right, now it's going to take some getting used to, okay? But here's my plus sign. Here's my minus sign, right? Plus sign, minus sign, plus sign, minus sign, okay? So this matches this. So that entire thing is my first term, okay? The 4y matches the 4y. That's my entire second term. So could I quickly multiply this by doing 7x plus 5 and then squaring it, and then putting a minus sign down, and then taking the 4y and squaring it? I could, all right? And then I could, hopefully you can do 7x plus 5, 7x plus 5. I'll write that down in your head. All right, I could do a 7x plus a 5 times a 7x plus a 5. And hopefully you could do that really, really quick. All right, what's that going to be? It's going to be a 49x squared, and then a 12x and a 12x. Ooh, I can't do that. That's a 35x and a 35x, which will be like a 70x. All right, and then a 5 times a 5, which is going to be a 25. All right, and then can I go ahead and write the minus sign down and then just square this term, which would just be a 16y squared. Okay, now you may not want to, if you're not catching on to this, you may not want to do it this way. All right, I think that way, if you can recognize it as faster, the other way would be what? Take the 7x times all three of these, take the 5 times all three of these, take the 4y times all three of those. Repeated distributive property would ultimately get you down to this anyway. But here again, all right, where are we going to go? In this chapter, we're putting everything together. In the next chapter, we're going to take everything apart. So in other words, in the next chapter, you're going to have problems like this, and it's going to say factor, and they're going to want to undo this process. And the only way to factor this is to be able to recognize this as the difference of two squares and then going backwards. So forcing yourself to do this method to multiply it out will help in the next chapter. Okay, I know that's coming, it's a long way away and you don't want to necessarily think about it, but it's going to be there. All right, now the only last thing I'm going to mention here just real quick is I am going to mention the difference quotient. It is a formula. I am not sure whether or not it's going to show up in tonight's homework for this section. However, it will show up before this semester ends. Okay, your book, there's several different versions of this. There's about 3 different versions, but the one in your book is going to be f of a plus h minus f of a all over h. Okay, so what this is the difference quotient. It lays the foundation for absolutely positively in everything in calculus. All right, we build the definition of a derivative from this. We build a lot of things in calculus from this form right here. All right, now it looks maybe scary, but if I cover up like all of this, isn't that f of a plus h just function notation? All right, and then if I cover this part of it up, I just see f of a. Well, that's just like f of x, except instead of plugging in an x, I'm plugging in an a. All right, so this really is no more than can you use function notation and evaluate some things. All right, they will start you out baby steps. They will let you just practice evaluating the numerator, and then they will build up to the entire thing in this course. All right, and like I said, it's about 11 after. I'm not necessarily going to do an example like this. All right, example of this, though, is on page 13 of the section 5-2 notes that are available to you online if you are in a hurry and would like to see it. Actually, page 13 and page 14 has a couple different examples on that. Okay. All right. So at this point, I'm going to stop sharing.